Welcome everybody. It's my pleasure today to introduce our speaker, Professor Stijn De Baerdemacker from the University of New Brunswick. So Stijn did his BSc and PhD degrees in physics at Ghent University. And then he came to North America for a reasonable period of time at the University of Toronto and Notre Dame, doing postdoctoral positions, and then returned to Ghent as, I'd say, more of a research associate and started doing some of his own independent work. And then 2 years ago, we have the pleasure of welcoming him to Canada, to the University of New Brunswick, as an associate professor in chemistry. And he has been recently, or relatively recently, appointed a CRC Tier 2 chair in theoretical chemistry. And Stijn's interests really are actually quite connected to what Igor just said, connecting these fields of high energy physics or nuclear physics, chemistry, and mathematical physics. And his real interest is in developing methodology for quantum many-body theory. And that's why I thought it'd be great for him to give a TPI seminar and connect with some of our colleagues in the physics department. So Stijn, please take it away.
Thank you. Thank you for the introduction. Before I acknowledge you, how can I share my screen?
Yeah, I think you should be able to share now. I've made you co-host.
Okay. Oh, I have a Firefox issue. I told you this was gonna be difficult.
Yeah, you should have a button that says share screen at the bottom.
Yeah, that's, oh, okay.
Is that working?
Okay, I think it's, okay. Okay, we're making progress?
Yep.
Now you're seeing yourself? That's already something?
Very good. And maybe you can...
and now we're going into slideshow.
Perfect.
Is that good?
Yeah, perfect.
Perfect. Are we in? Cool.
Yeah, go ahead.
So yeah, first of all, thanks a lot to Alex for inviting me. We already had met a couple of times since I rejoined Canada. So yeah, I did a postdoctoral stint, let's say, at the U of T with, maybe some of you remember David Rowe. He retired some time ago and he passed away recently, very sadly, but he's a nuclear physicist just like me by training and turned into a mathematical physicist. So at that time, but I'm gonna go into that a little bit more in the next slide. Because first of all, I want to say thank you for inviting me. I love to interact with people in the sense that my interests are very, very broad. What I'm going to be talking about today is like a subset of what I've been up to in the last couple of years, but it stretches way beyond that. Okay, so as I'm new to Canada, and I'd like to introduce us and myself a little bit. So like Alex said, I am a nuclear structure physics PhD in 2007 from Ghent University. So I moved on to work at U of T. I thought I was going to become a mathematical physicist. That, in retrospect, I don't think that was really what I was going to become. So I realized I made some contacts with Paul Ayers from McMaster, and turned out that actually I had a very keen interest in quantum many-body theory, and more in particular with the electronic structure problem for molecules, next to the stuff that I was doing at the time. Okay, so I was very fortunate to when I got the opportunity. Yeah, when I got the opportunity to become a Canada Research Chair, I immediately took that, acknowledged that, and made the jump once again. And during the COVID period, so this is the only group picture that I have right now, simply because, yeah, you know the circumstances. So the idiot on the bottom right, that's me. and all the others are serious and very promising researchers, young researchers. Okay, so what do we do right now? It's a bunch of like a wide variety of stuff. So the topics that we're working on are on the bottom right there. So I came in, I think, on Geminal theory. I'm going to be listed in blue because I'm going to be talking a little bit more about that topic today. With Amir, right, upper right picture, with looking into some symmetry breaking methods, ideas into quantum chemistry. So this is an idea that I've blatantly stolen without any shame from nuclear structure physics, and I think we think that there is some good, let's say, interesting analogies in electronic structure theory. At Ghent University, I did a very short stint into condensed matter physics, and from there I took the tensor network states, which we are now looking together with Mostafa in trying to apply or looking for the application in more, let's say, biological driven systems. So that is going to be quite an adventure. Obviously, we're also looking into, it's also listed in blue because I'm going to talk a little bit about that in today. Machine learning, mostly because everybody is doing it. So Ahmed, Claire, and Mai, which are the upper left pictures, are working together with me, PhD and undergrad students, on not so much in yet the so manyest application of machine learning, but more in why they actually work, right? So why are they so successful? Why are they taking us by storm? I'm also looking now for, so if you know any good candidates for grad studies, I'm also looking into new projects on non-equilibrium electronic dynamics in molecules and combining that maybe with some quantum computing. Okay, but today I'm going to be talking about Geminals, okay? Electronics, an old electronic structure problem that we rekindled in some way by tying it in with the concept of integrability. Okay, so as this is the theoretical physics, what is it, initiative? I don't know. Institute, I thought you will not be too scared if I drop those bombs, integrability, and I'm gonna insert some equations, a little bit more equations than I would normally do. But I will tie this all in within the general problem that we're interested in, and that is the quantum many-body problem, or the finite quantum many-body problem. Okay, so why do we do what we do? I've given here two systems here, two very interesting systems on this slide, and they are very different in nature, but they are, let's say, plagued by the same sort of problem. Okay, so on the left you see amyloid beta. It's a protein, and it is a protein that is situated in our brain cells, and turns out that it's very correlated with Alzheimer's disease. Okay, so what happens if a post-mortem dissection of people that deceased from Alzheimer's disease, they will find that these amyloid beta proteins, they would form like plaquettes, and these plaquettes, they would build up together and they would sort of like pierce through the cell membrane of the brain cells. So obviously this is not supposed to be the case. So there's something went wrong there at the dynamics level of this protein. So trying to get a hold or getting an understanding on how these very complex systems work from ab initio is one of the major, I would say, challenges of theoretical chemistry and theoretical biochemistry. On the right-hand side, you see a Taken complex. I'm not a chemist by far, so I cannot really entertain you much on what the chemistry was going on there, because actually I'm a physicist, and as a physicist, then I'm looking at spins. So this is an iron complex, has a lot of spins, and it has a molecular magnet. So it's a magnet at the molecular level. So it's a very interesting compound just to think about it in terms of a memory of future devices. Okay, as we scale down the memories or the sizes of our devices, at some point we're going to hit the molecular level, and then we're going to be looking at those sort of systems. Now, this is a spin system, has many degrees of freedom. They can interact with each other in a myriad of ways, a myriad of states, quantum states that can coexist with within and trying to get a good quantum mechanical let's say characterization of this system is going to be very important in the future for such sort of things. Well, I have to say here that I have, whereas this is the goal, I hope maybe in my retirement I will be able to treat this sort of system, that we have solved these problems. But I'm not, let's say, I'm not confident that I'm going to be solving this in the next couple of 5 years, or maybe not within the term of my CRC. So how are we going to do this? Well, they're challenging problems, right? So that's why we're interested in them in the first place. So what is the job? Okay, so the job is basically rephrased in 2 lines. Okay, the mission of a quantum many-body theorist is, 1, you construct the A-body Hamiltonian, because sometimes it's not given. Chemists are pretty lucky in the sense that we are given the Hamiltonian, but in some cases we're dealing with effective Hamiltonians. Think about, for instance, the protein problem. This could be described in terms of an effective Hamiltonian. It would also have to involve many body terms that go beyond the standard 2-body interactions. And then what you do, you just have to solve the A-body Schrdinger equation and you're done. You go home. Okay, so then comes in Dirac, Paul Dirac, and Paul Dirac in the 1920s, the end of the 1920s, have made a very interesting statement in one of his, let's say, defining papers. It's like one paper after defining paper, one after the other, that he's written in a very short period of time. And I think this must have been the last one. And I'm going to just read with you through the quote what he said at that point. The fundamental laws necessary for the mathematical treatment of large parts of physics and the whole of chemistry are thus fully known at that point. Okay, he was talking about the Schrdinger equation. And the difficulty lies only, note the only, in the fact that application of these laws lead to equations that are too complex to be solved. Okay, so this is a quote that he made 90 years ago almost. And I think this quote is still the thing that keeps us busy or keeps us up all night. So what does it mean? Too complex to be solved? Are we just too stupid to solve difficult partial differential equations? The answer is no. Okay. So to get an idea of where the complexity, or where the complexity of the problem or the complication of the problem is, can be, I think, well understood by means of this little cartoon that that I have here. So let's say we're thinking about a molecule and we have some charges, okay, some positive charges, some nuclei, and these are these red blobs, okay. And now what I want to do is I want to distribute some electrons around these blobs, okay. So how are we going to do that? So the first thing you can do is you can create a grid, okay, or a lattice if you wish. But you have a grid of boxes, okay. And this is just to make it discrete, just to make it easy for me to put it into a computer. Now I have this grid. Now what I can do, or have to do, is distribute electrons over these boxes, okay? And I know about the Pauli principle, so I'm only going to put 1 electron in each box. And then I can have a distribution, let's say like this, okay? So this is a configuration that appears not too crazy, okay? So charges are surrounding the nuclei, they're well distributed. You even could see some sort of like a shell distribution there. But this is a configuration that is classically viable, okay? So I would call this a classical configuration, or a slated determinant, if you wish, okay? Now, we're not living in a classical world. We're living in a quantum world, so there are other that are also possible, okay? So this one appears to be equally possible. There's no way why this one would be much better than, for instance, this one. And I can continue like building all these different redistributions, okay? around these nuclei. Okay, some of them will be less important. So this one, for instance, I don't see this one to be becoming that important. But you can feel this problem, right? So I can make a combinatorial amount of configurations that appear to be equally feasible or equally possible. So in a quantum world, so where we have a wave function, each of these classical quote-unquote configurations are sort of equally viable, equally possible. Okay, so I have to make an expansion of all of these Slater determinants, so say classical configuration, and that is a combinatorial problem. And okay, that's fine, it's combinatorial, but how bad can this be? Well, you have to take a look at this particular plot that I've made here. So what is given here is the dimension of the Hilbert space, okay, so the number of classical configurations you can make as a function of what we would call basis states, L. Think the number of boxes, okay, for a number of molecules. So I've listed there methane, hydrogen gas, iron, just the atom, there's benzene, my favorite one, caffeine on the right, okay? So each of these curves have a specific number of electrons, 2, 6, 10, 26, or 102 for caffeine, that I can distribute over a number of boxes. And as I increase the number of boxes, the number of possibilities, then I also get an increasing number of allowed states, okay? Now notice on the left that I have plotted this in a logarithmic scale, okay? So, and for a reference, in red, what you see is the amount of numbers that I can store in 1 gigabyte RAM, okay? So what you see is this is just the vector, just being able to store that wave function. You haven't done anything on that yet, right? So for that, you would need like the square of that, but just the vector. So what you see is that with hydrogen, you're fairly okay, right? So this is also the reason why we love hydrogen. You can always do something with it. But with methane, as soon as you start to like wanting to do a little bit more than just like a very schematic, you run out of steam. Iron becomes, runs quickly out of steam. Benzene, just adding a few boxes and you're hitting the roof, etc., etc. So this is really becoming a problem, okay? We don't have the capacity to just store these vectors, to store this amount of information. Now you can say, okay, fine, you're just gonna wait for your Taken compound there to kick in. Moore's law is gonna give me another degree of freedom, it's gonna give me so much more power, but this is a logarithmic scale. So I'm just gonna, in a few years, I'm only gonna be able to push this red bar a tiny little bit higher. I'll never get to, let's say, 10 to the 20 or something like that. So this is a losing game. This is not the way to go. Adding computational power is not the way to solve this problem. Okay, so what do? You let the physicist in yourself get loose. So you look for the simplest toy model that you can do, and that is the hydrogen molecule. As a physicist, you simply have to fall in love with the hydrogen molecule, simply because you can do everything on a piece of paper, on a sheet of paper, back of the envelope calculations, and you basically get most of the physics out of there. Okay, so what you see on the right-hand side? So what you see on the right-hand side is a typical quantum chemical calculation. So you choose a configuration in the Born-Oppenheimer approximation of your nuclei. Okay, so R in this particular case means the distance in which I put the two hydrogens apart. Okay, and then I'm doing a calculation for the energy. So I want to know what the energetics is of this particular system. So I can do that for as a function of the distance between the two hydrogens, as the bond, let's say, as the chemistry, as the bond breaks. And then you have three curves, and I've chosen these because they're like emblematic or paradigmatic models or paradigmatic calculations that you can do in quantum chemistry. The green one is the full CI, so that's the full configuration interaction. Take all the configurations that I need, do a full-fledged diagonalization, I get the result. Okay, so that is the reference curve in this particular case. Okay, then you can compare this with the blue one, that is a self-consistent field. That would be the Hartree-Fock calculation, if you've heard about the name. And you can see there, this only takes one configuration and optimizes that configuration. You see that you're missing the energy like with a factor of 2. And so an experimentalist would not be happy with your prediction of the dissociation energy of hydrogen in this particular case. And then I've also put a PBE functional, a density functional theory calculation. We're going to talk about density functional theory there. It's just for completeness sake. But it's a very popular method that's being used right now for a lot of applications, and it also fails to get that curve qualitatively right. Okay. So what you do, you take a step back and you try to look at the physics. Okay, so what's going on there? Okay, now what is going on? So you have two hydrogens, my left hand and my right hand, okay, and they both come with a set of orbitals, SPD orbitals, let's say. If they come close, then these orbitals are going to start interacting with each other. Okay, so you get a level repulsion. Okay, now the low-lying ones are the bonding orbitals. Okay, or the one that bind the molecule, whereas the upper ones are the anti-bonding ones. As long as they're sufficiently close together, let's say at around 1 Bohr, then both of my electrons want to be in the bonding orbital. And you can see this one classical configuration, the blue curve, Hartree-Fock curve, is doing a fairly well job at equilibrium. So there, a single reference framework works pretty well for you. It's only when I'm starting to stretch the bonds that the bonding and the anti-bonding, so the repulsion, the level repulsion starts to diminish, they start to become degenerate. And this is where these two different configurations become equally important. So you're starting to create a resonance between the bonding and the anti-bonding. So this pair of electrons starts to hop there. And both configurations become equally important. And this is why this self-consistent field, which only takes one configuration to occur, fails, whereas you need those pair resonances to get this right. Okay, so pair resonances. So the idea is, why don't you try to capitalize upon these pair excitations? So this is an idea that's been introduced, I would say, in nuclear physics in the 50s, but has found a way into chemistry only, let's say, 10 years ago by the work of Schrdinger, in which you try to reorganize your Hamiltonian, which is given up in that equation in second quantization, in terms of seniority. Now, what is seniority? Seniority is the number of particles that are not coupled pairwise together. Okay, so if I have a seniority 0, it means that all of my electrons have a best friend forever. What is the best friend forever? Typically, it is the same electron with the spin down in the same, it's an electron, the brother with the spin down for the spin up component in the same orbital. Okay, so the nice thing about that, about the seniority quantum number, is that it also generates an algebra, an SU2 spin algebra or quasi-spin algebra via the pair creation and annihilation operator. So you have a seniority quantum number is a real quantum number as in a mathematical sense, in an algebraic sense. Okay. And what does this quantum number allows you to do is to reorganize your Hilbert space or your configurations a little bit. So what you typically would have is you go, in a standard theory, you would go from left to the right, okay? So you would start from a single reference state, think your Hartree-Fock, which is a 0 particle, 0 hole. And then starting from there, you start to create particle hole excitations of, with respect to that reference state. And as such, you can build up your whole hierarchy of your Hilbert space, okay? Now, the seniority quantum number tells you not to go from left to right, but to go from up to down, right? So where you would break one pair one at a time, okay? So you would start from a seniority 0, where everything is paired, then go to breaking one pair, breaking 2 pairs, etc., etc., etc. Okay, so Schrdinger and collaborators did this, and Baitautas and collaborators did this for a typical paradigmatic paradigmatic model for strong electron correlation. Is the same as a hydrogen that we looked at, but you put so many in a chain, okay? Condensed matter physics friends would call this the Hubbard model with 8 sides. It's completely similar to that, okay? So you do a calculation, you have 8 hydrogens sitting next to each other, and then you sort of like you bring them further away from each other. And so this would be equivalent with increasing the U parameter in the Hubbard model. And you look at what the energy is. So, and how you do it, you do a calculation in the seniority scheme, okay? So you start from the seniority 0, which would be the blue curve here. So you would only take paired configurations into account. And then you gradually allow for broken pairs. And you go to the brown curve, to the green curve, and you see how quickly this thing converges towards the exact value. So this pair idea is really valuable, okay? So from we would say that these DOCI, so doubly occupied configuration interactions, this is a name for the method if you only take seniority 0 into account, no broken pairs, is very good for static correlations in which the entanglement between bonding and anti-bonding orbitals is very important. I mentioned here dynamic correlations, which is probably not so, I won't go into right now, but I'm going to come back into that later on into the slide, because you can already see a caveat there, a frowny smiley that, that warns us of a couple of things. Now, probably the biggest warning is at the bottom, okay? So I take the lowest rung on the seniority scheme, or this partitioning scheme, okay? Turns out that the dimension of the seniority, so how costly is this calculation? Well, it's a major reduction because I can do this calculation, this fairly accurate calculation, at the cost of only the square root of my original dimension, okay? So I have my full CI, all possible configurations. I only select those that are paired, and I can make a reduction that goes like the square root of this dimension, of original dimension. Now, that was the good news. The bad news is that the square root of an exponential is an exponential. So, no good, okay? So this is not a good way to go. Now, but you do want to keep that pair picture. So what do you think? So the first thing we then always we do is like, okay, let's go for a mean field picture, okay? So let's go for a mean field. We know a mean field picture in terms of the single electron, so that's the Hartree-Fock state. But what if we just build a mean field picture in terms of the pairs, okay? Well, if I would do that, then I would have a product of generalized pair creation. So S dagger is one of those pairs. It's an SU2 generator, as to say, but you can see it as a pair creator. And I'm dressing that, okay, over all possible boxes, over all possible orbitals, and I'm taking a product of them. So how many of those factors do I take? Well, as many of pairs that I have. And I call it a Geminal state. Now, I didn't call that a Geminal state for the first time. People like Hurley, Lennard-Jones, and Popel, those are like famous names in the community. They realized that you should be looking at quantum states of this particular type if you want to look at pair excitation, if you want to look at Lewis structures, right? Because this is what a chemist does. So this is caffeine. All of our favorites, this is the favorite molecule for me and for any theoretical person. What we do is we draw these lines. And what do these lines signify? They signify bonds, okay? And these are pairs, Lewis pairs. So Lennard-Jones and collaborators, they realized that this would be the way to go. Now, this took off in the 50s and it immediately died. And why did it die? Well, the reason is this wave function is simply computationally intractable. What do I mean with that? So here is a Geminal state, upper left, okay? So it's a product of generalized pairs. And I want to do something. I want to store this thing in my computer, okay? I want to store let's say, projections on slated determinants. I want to store numbers, okay? I want to store amplitudes of certain configurations. So what do? I take the overlap, okay? So I take the overlap of my APG, my Geminal state, with respect to my slated determinants. And what happens there is I have to take the permanent of the Geminal matrix. Okay, so what is the Geminal matrix? The Geminal matrix is this matrix G that you see in the factorizable form of the matrix. Okay, so you take a square matrix out of those. It's in general it's a rectangular one, and then you try to calculate the permanent. Now this is usually a moment where I interact a lot with my audience, because then I ask if anybody knows what a permanent is, and once in a while there is somebody who knows. But then I start to explain that the permanent is the symmetric brother of the determinant. Okay, so a determinant, the formula of the determinant, well known, is given up there, and some overall possible permutations with a sign of the weighted with a sign of the permutation. Now a permanent doesn't have that, so there is no pesky sign, right? So you don't have to worry about signs. This is so simple, so easy. You just write down all the permutations. Now, turns out that calculating the permanent of a matrix is probably the most vile computation, or the worst complexity class that you can imagine. Okay, simply because the determinants. You can calculate the determinant because you can make a connection with linear algebra. You can do Gauss elimination there. But with the permanent, there is no such tricks. So the only way to calculate a permanent is via the Laplace expansion. Okay, and the Laplace expansion is scales n factorial. Okay, so this is an n factorial scaling problem. And what is even worse, it is a complexity class on its own. I think it's called P sharp, because verifying afterwards whether you've done any errors also scales n factorial. So this simply kills your Geminal project because you cannot evaluate this thing. Okay, so that was the status before all these bunch of people met together. Okay, so this is a collaboration now. How we tackled this is this Geminal problem, or how we put a new wind into this Geminal problem, is basically the effort of all these people combined. And what you see, we are a funny bunch, because we consist of physicists and chemists, condensed matter physicists, Jean-Sébastien Coe, quantum chemist Paul Ayers, Patrick Bulting, some nuclear physicists as myself and Dimitri Van Eck, some real chemists as Paul Johnson, Pavel, Katarina, Kasia, and Klaas, who's a physics engineer. We all sort of bundled our brains together to get Geminals on the rail. Now, what was the central idea? Integrability. Okay. So how is that? So I'm going to shift gears a little bit here. So what is integrability? Integrability is a symmetry. Okay. And I'm going to use a very loose definition here, because you can start debating about what an quantum integrable system is for many nights, and I'm not going to do that. I'm just going to use this very simple definition. So a quantum system is integrable when its Hamiltonian supports as many conserved quantities as there are degrees of freedom in the system. Okay, and then the debate is obviously what you mean with degrees of freedom in the system. And in our case, this would be the number of boxes. Okay, that would be the degrees of freedom that I am talking about. I'm sure you've heard about it. Integrability. I'm sure you've heard about the beta-ansatz solution to the Heisenberg model, which is a model for 1D magnetism, which has also been verified experimentally in these potassium-copper compounds. It also occurs in the Richardson model, which is, funny enough, an exact solution to the BCS Hamiltonian, as it was written down originally by Bardeen Cooper and Schrieffer. So it also takes, there is an integrable model that can describes pairing correlations. Okay, and this is interesting, right? So what are these pairing correlations? Can we maybe exploit a few features of that symmetry? in our benefit. Okay, so how does it work? So yeah, this is a particular category of integrability. It's called Richardson-Gaudin integrability. So you may have heard about the Gaudin branch of integrable models. Basically, an integrable, well, the Richardson-Gaudin model is a model which is built up from the linear combination of conserved charges. Okay. So we have a Hamiltonian, that's a sum over all operators R, and the condition that I put, or the constraint that I'm putting on these R's operators, is that they commute mutually for all of the boxes. Okay, so I and J, they run over all my orbitals in this particular case. So how do I go about with this? So basically I write down an ansatz for these operators. Okay, so they're given up there. And you sort of recognize a spin-spin interaction there, okay? And as a matter of fact, it is a model for the central spin model, where you have a red spin in the middle that is interacting with the bath, and the spins of the bath themselves, they don't interact mutually. So it's sort of like this one central spin in the middle that is sort of like mediated by all the spins surrounding it. It's well, people are now looking into this is a model for the NV vacancy in diamond. You can model by means of this one of those conserved charges. Okay, now so you impose integrability on. So I have three parameters, xij and zij, and now I impose integrability, and this gives me conditions. And they are given by the bottom equations. Okay, so this is a set of equations that the x and the z's must fulfill, must obey. We call them the Young-Baxter-Gaudin algebra. Young-Baxter it's a variation of the Young-Baxter equations that you may have known, that you may have seen. Okay. So how do I visualize that, or how do I make sense out of that? It's an algebra. Okay. And there are different representations that you can think of. So either you can look at them in terms of a matrix representation, where they're just like matrices that fulfill these element-wise. So there's no contractions there. It's really an element-wise algebra. They're just matrices, and you try to find numbers in this matrix. You can look at them in terms of diagrams. Okay. It's a little less practical in terms of numbers for numerics, but it's very, I mean, it's cute when you try to prove lots of identities, right? Then you just draw these great diagrams. Or, which is very useful for analytic stuff, is there's even a functional form. So you can prove that a set of x and z in order to fulfill the Young-Baxter-Gaudin algebra, it necessarily has to have this particular shape. Okay, so this problem is basically solved in terms of the structure of the algebra. Now, what does it mean for the Richardson solution? So what does it mean for the integrable models, right? So the Hamiltonian and the wave functions, the eigenfunctions that go with it. Well, that's basically sorted out by Richardson. And so you write down the Hamiltonian in terms of all these conserved charges. Turns out that if you do the algebra, that you end up with the BCS Hamiltonian. Okay, so there it is, with G completely free, but level independent. Okay, so that is crucial. You can see there, I have as many free parameters as I have boxes. Okay, so I have epsilons that I can choose freely. Those are given to me by maybe experiment, maybe a Hartree-Fock calculation, maybe something else. Okay, so that's the Hamiltonian that was known by Barty and Cooper and Schrieffer. Now what Richardson has done, he has basically written down a wave function, a beta ansatz wave functions, unknowingly, because he was not aware of all that work, as a product wave function of generalized pair creation operators that you see on the right there. So I have an S alpha dagger, which is a linear combination of single particle operators, single particle pair creation operators, and I take a product of that. Okay, sounds familiar? Yes, because this is actually a Geminal state. Okay, and I dress these with generalized energies, X alphas. Okay, Now, if I plug this in my Schrdinger equation and I require the state to be eigenstates, then this put a condition on my generalized energies x alpha. My x alpha coordinates, they need to obey the set of Richardson-Gaudin equations, okay, that are given at the bottom. Why is this important? This is important because look at how many variables that I have. I only have n variables. So with each pair, I have a variable. Each pair is described by one particular variable, and I have to solve a nonlinear system that scales linear with the number of pairs. So suddenly I don't have an exponential limitation anymore. I can let this thing blow up. I can do Richardson-Gaudin systems with millions of electrons, millions of pairs, opposed to exponential of millions. Okay. So yeah, that's fine, but that's good. It's mathematically good, but can you really use this? Is it sensible? So this is the first thing you have to check, whether this could be a good wave function for chemistry. And in order to do that, you can look at this toy model. So what I have here is on the bottom left is, let's say, an optical lattice. Okay, so I create an optical lattice and I throw in electrons. Okay, so I'll throw in 52 electrons, and there's like 80 single particle levels that I can choose. Okay, 80 single epsilons. And I tune my interaction such that it is there's a so there is this Richardson Hamiltonian there. Okay. So how does it work? My wave function is on the left. I have to find my x alphas by solving this equation, by solving the Richardson-Gaudin equations. So my epsilons are given in the blue dots, and here are the x alphas. Okay, these are the red dots. So this is a wave function. Okay, each of these red dots represents a pair, an electron pair. It is in the complex plane. Okay, but they always come together. So together they always make a real pair. Good. What you have to take away from this picture is that you can really, this is a very collective wave function. This is a very, let's say, if you would do the expansion in the singles and the Slater determinants, you would end up with, as a matter of fact, an exponential scaling number of coefficients that would be important. Why? Because the red dots are relatively far away from the relative spacing between the blue dots, between the single particle levels. Okay, I threw in just some numbers, so R, which I'm going to talk about in a minute, and G. So G is the interaction strength. So what I can do is I can decrease the interaction strength. And what you see is that these red dots, they go back to the real axis, and they're going to pick out a single particle level. Okay, so they go back to, let's say, they're going to go pick out one epsilon, and they're going to sit there close and sort of like single out that state. So this becomes much more a mean field state. Okay, and you can do that until you've like gradually turned off the interaction, or almost turned off the interaction. Okay, G, the interaction strength, is one parameter. This is not so much chemistry. What is more interesting in chemistry, if you would do a bond breaking. And how can you do that? Well, I can change the spacing between my welds and the optical lattice. Okay, so what I'm going to do is I'm going to push this one out. And you see a similar sort of behavior, and I've rescaled it a little bit, my energies. And as I go, I see that my single particles, so my x alphas, they're going to redistribute again away from the single particles, but they're going to do this in two bunches. Okay, so they're going to reorganize around a bunch of orbitals that are bonding and that are anti-bonding. Okay, so yes, we can recapture that typical bonding anti-bonding procedure from that we need. Okay, so this is cool. Okay, so this is really exciting because now we have a wave function that we can calculate, and that is potentially viable for bonding anti-bonding dynamics. Okay, so we're very excited. So what's the idea? The idea is now to reconsider our many body theory. Not start from uncorrelated basis functions, but start from correlated basis functions. These Richardson states, these Geminal states, these special Richardson Geminal states. So yeah, this is a little bit of a poor picture. I'm not very proud of this, but this is supposed to represent a correlated wave function. I'm just going to skim over it because it's misleading at best. Okay, but if you want to do that, you're still trapped with that permanent, right? Remember, we had a Geminal state. If I want to do anything, I end up with a permanent, and this is factorial scaling. Okay. Now, not so much with Richardson. Okay. So as soon as you have this integrable system, when you dress it with integrability, what you will have is if I take the overlap with a slated determinant, this permanent reduces to a ratio of 2 determinants. Okay. And this is by means of this is a result from the 1800s by it's a German. I don't know how well your German is, but it's a very nice paper to read. It's actually pretty readable still after 150 years. So, but nevertheless, the result is there that you can rescale this permanent as a ratio of 2 determinants. So we are in business again. So we have something, a Geminal state, which we can really do some computations. Even more stronger, we can take, I call it off-shell Richardson-Gaudian states with respect to a Richardson state. And again, this is a determinant of a matrix, which I'll call the Slavnov matrix. It's a result that comes from the integrability, the inverse scattering community, Nikita Slavnov. But the important thing is it's a determinant. And it means that we can now calculate overlaps. We can do a variational theory with Geminal. So that is really, that was something, okay? So this is exactly what we did, okay? So we use Richardson states as variational Geminals, okay? So this was probably one of the first variational calculations with, and that was scaled up a little bit. So what do? You construct a manifold of in L-dimensional space, L the number of your boxes, and you can optimize your parameters, the epsilons, such that your energy gets minimum of the Hamiltonian that you wish, with the constraint that you remain integrable, okay? So that your X alphas, your pair energies, remain on this integrable manifold. So on the right, this is a calculation by Pavel, and this is typical quantum chemistry calculation. So you see a figure with all sorts of like potential energies, and then you have 50 acronyms. Okay, so I'm gonna talk to you a little bit through the acronyms that are important. So the blue one, it's covered a little bit in the back, is the reference, is the full CI. So this is what we aim for. Okay, we did APR2GA. Okay, that is our Richardson state. It's a gray dotted one. It's a little bit remote from it. We do better with B. So the difference between A and B is a different orbital scheme. I'm going to come back to that. A little bit better, but not quite still on the full CI. So a little bit disappointing. But what we did find are other states like ooh, AP1 rock, PTA, ooh, AP1 rock, PTB, that are just spot on that blue curve. Okay, so we discovered, let's say, a new type of Geminals in the process. And I want to talk a little bit, the time that I still have, about that one. So what is AP1 rock? It's basically you take a Geminal and you go couple cluster with it. Okay, so you project it, you don't solve it fully, you solve it projectively. Okay, so it is a Geminal state, and it's, let's say, it's half correlated. Not fully correlated, it's half correlated. It's correlated in the either in the virtual or in the occupied space. And you do the calculation. So this is the hydrogen chain again. So you stretch them. The reference curve is in black. Couple cluster has a couple of glitches. That's CCSD. Hartree-Fock again goes through the roof. And our new method is actually basically has the same quality as this DOCI that I talked to you earlier, with the exception that this one scales polynomial, has coupled cluster scaling. Okay, so that is interesting. Okay, so you start investigating that wave function a little bit more. Turns out that you have to optimize your orbital scheme. So everything is dependent on your orbitals. Okay, so how you take your orbitals. This is simply because if you're rotating orbitals, you lose the pair structure. right? You're breaking the pairs. Once you do orbitals, you try to rotate over your orbitals. What is originally paired together, you're distributing independently, you're going to pick up pieces that are not paired together. And your results can vary very strongly depending on what orbital scheme you're using. You can see a calculation by one of my former students. And depending on what orbital sets, you can see Mo, and it doesn't really matter what it all is, you can see that the results are fairly different. Now this has an advantage, because if you take the optimized ones, energetically optimized ones, you end up with an orbital scheme which is, for a chemist, very intuitive, because it drives you to what we call sp3 hybridization. Okay, so if you look at let's say methane, okay, then the orbitals that give you the best results are the ones that are in line with the bonds between the hydrogen and the carbons. Okay, so you know that, and this is from your chemistry classes, you have the p orbitals and the s orbitals, and they are like the x, y, z coordinates, and they mix together and they turn into this tetrahedral case. Okay, if we just run the machinery, black box, these were the optimal orbitals that were in line with the pairing structure, which is not totally surprising, but it is encouraging, right? That you get this sort of results. Okay, so that was all fun, and we were enjoying ourselves very much. And we push it a little bit further, and we start to see dark clouds popping up, right? Because nothing's perfect, right? And we realize that as long as we are dealing with single bonds, bonding, anti-bonding can be very entangled, very intricate structure, we're doing fine. But as soon as we're trying to probe this, going a little bit out of that, let's say, organic, well-behaved stuff, that we start to see deviations. Okay, so we call that, yeah, it's a bit of a catch-all. I'm not going to go deep into that, but dynamic correlation, the competing correlation due to, well, Coulomb repulsion is bothering us. And we see this in triple bonds, orbital resonances, and also a little bit in dispersion. And the last final time of my talk, I would like to spend a little bit about that, if I may. So we have a case study here, okay? Benzene. Benzene, you've hexagons. If you're into hexagons, that is what benzene is. Benzene is interesting because it has a very interesting resonance structure. And so if you look at valence bond structures, basically with 5 structures that you can see up there, you're good. Okay, so you can, valence bonds is very successful in describing this thing. Now, if you look at the Kekulé part of it, on the upper left, you see that I have double bonds that I have to choose. There's a symmetry breaking there, right? So either I'm taking the odd bonds or the even bonds, okay? But I need both. But if I'm doing an orbital optimization, it's going to choose. It cannot choose both. It has to choose one particular configuration. So it's either going to choose the left one or the right one. And this preference we're going to see if we artificially break the D6H symmetry. So if we break that symmetry of benzene with respect towards D3H, okay? So that's the curve that you see on the right, okay? So we have the angle theta. Theta is defined as, let's say, the deviation between D3H symmetry and D6H symmetry. So 60 degrees would be a perfect hexagon. And we know from experiment that this is a stable configuration. And this is also seen if you do couple cluster single doubles, MP2, Hartree-Fock, all the colorful curves, except our wonderful AP1 rock, where that dictates a symmetry breaking. So there's something wrong there, okay? So we gain some energy, but it's wrong energy, or the wave function is wrong. Second case study, nitrogen. Nitrogen gas is always a pernicious case. Why? Because it has a triplet bond. How do we understand that? If we take nitrogen as an atom, Hund's rule tells us that it wants to couple the 3 electrons and the p orbitals. They want to couple to 3 halves, spin 3 halves. Okay, so I have spin 3 halves up here. Now the molecule N2 is a singlet. So it couples with the other 3 spins like this. Okay, so we know that this is the wave function if we totally stretch it. Okay, now this sort of signifies that I would need 3 electrons that are lone electrons that don't pair together. So my seniority decomposition tells me that I need a seniority 6. Now, okay, so this is the p orbitals that I have. I can probably optimize that. So let me do that. So let me try to optimize my orbitals such that the seniority is as low, that they pair up as much as I can. And if I do that calculation, you end up with figure number B, where the full curve, the reference curve, is V10. So that is the, let's say, the crosses on the very bottom. Okay. And the seniority decomposition is given by the different symbols. So you started with the blue triangles above. You add 1 broken pair, nothing much happens. Then you add 2 broken pairs, and suddenly you tumble into this seniority 4. Okay, so you need 2 broken pairs at least. And then you can converge. Okay, but these are the optimized ones. So I can't do any better. I can't do any better than that. So why is that? So we built this toy model in which we basically made, starting from our p orbitals that are localized on the nitrogens, we sort of made them more molecular orbitals that would describe the bond much better. And if you can describe the parameterize that by means of this angle theta again. So if you do that, then theta equals 0 would be the triplets, the seniority 6, whereas theta pi over 4 would be the molecular orbitals. Okay, so the one that would really describe you the bond. And then you do a calculation, and then what you see is that everything is sort of the decomposition of the coefficients. You see that either you have a seniority 6 or you have a seniority 0. When you optimize that at the center, it comes at the additional cost of having a seniority 4. So you'll never be able to have a pure paired wave function in nitrogen, simply because of the triplet structure. Okay, so you try to fix that, and then you open up your toolbox, and there's so many different methods that you can do to get in this dynamical correlation. So you can do perturbation theory, you can freeze some pairs, you can go linearized coupled cluster, you can do some selected CI, which is given on the right there, where you extract some configurations that you wish, RPA, whatever. Okay, so there's a bunch of people jumped on it, and they have been testing all this sort of approximations. What we did, and this is, I hope, if I can spend 5 more minutes on the density matrix normalization group to analyze this a little bit further. So what is DMRG? DMRG is, it starts from the idea that all correlations are local, okay? And that a wave function is characterized by its entanglement structure. So you take your different boxes, or let's say the little boxes within your big space, and then you say that they're all entangled together, okay? And this entanglement sort of signifies the bonding, anti-bonding structure there to some extent. And you can make that mathematical by MPSs, matrix product states. So condensed matter community is very familiar with that sort of representations. And you know that it can converge to the full CI limit if you work hard enough, if you have that bond dimension, if you increase that sufficiently large. And it has the additional advantage that you can use a graphical notation. And so there's a lot of calculations you can just do by drawing some pictures. So that's pretty cool. This present state of the art is we can deal 40 electrons in 40 orbitals with this, which is pretty neat, actually. Probably we can add a little bit more. So what did we do with class Gunst is use a seniority quantum number. With these tensor networks, okay? So the bond dimension now goes with the seniority. As we increase the bond dimension, let's say, we increase the seniority. We can gradually take into account these broken pair configurations in a very systematic way. Okay? So this is, it allows us to identify the importance of these broken pair correlations. So you've already seen this one, this figure from nitrogen. that was a calculation that we did with DMRG, in which we gradually opened up broken pair configurations. And turns out that if we really want to capture the dynamics of nitrogen gas, we really need to include seniority 0 with seniority 4. So we really need to take broken pair configurations into account. It's not a perfect pairing system. Here is benzene again. So same question. What will happen to the symmetry? Will we restore the symmetry as soon as we include broken pair configurations? And this you can see on the figure. So it's a little bit of a dense figure. Ideally, the minimum should be on the right. And as we move up in seniority rung on the ladder, we go from the blue triangles all the way up to the crosses. We can see, as a matter of fact, that the symmetry gradually gets restored with, let's say, the most important shift is the V equals 4 and the V equals 6, which sort of signifies, again, that we can have a, let's say, seniority 6 broken pairs, that 3 broken pairs, 6 single electrons that need to be taken into account. Same story with dispersion, but I'm not going to go back into that. Dispersion is an interaction that is induced by means of dipole interactions, and it's very sensitive to very tiny little details. Pair method will never get you a bonding neon dimer, but including broken pairs does so. Okay, so this brings me to my conclusions. I've overdone my welcome, I think. So my conclusions are there. Geminals do their job. Okay, they sort of capture the heap of the important, let's say, bonding anti-bonding correlations. So at a very reasonable computational cost. But then again, you also have to take into account that nothing is perfect, so that you also have to take other things into account that go beyond the simple picture. Okay. And leaves me to acknowledge my funding, which is the Canada Research Chairs. Very grateful for those. UNB also put in some money, NBIF, the local provincial one, and some money that still came in from Belgium that supported class. So thank you very much for your attention. If you're interested in this whole integrability story, I've given a week lectures Monday morning to Friday night at Saclay, in which I've basically covered everything about this whole integrability thing. So all my lecture notes are still online. So yeah, with that, I'll leave it. Thank you very much.
Thanks, Stijn. So I know we're a bit over time, but I'm sure that we'll be happy to answer questions. It's easier when these are at 4 p.m. and go till 5 p.m. or so. But if people have questions, please feel free to either type into the chat or unmute yourself and ask your question.
I had a question, actually.
Okay.
Could you please go back to your slide on the Richardson-Gaudet model? I just wanted to understand. Oh, I guess you stopped sharing.
So there we are again.
Yeah, I guess I just wanted to understand how this N is related to L, and then the meaning of these X alphas.
I should be there in a second. So which one do you want to see?
Yeah, well, basically the slide where you had the Richardson-Gaudet and Hamiltonian.
This one. This one.
Yeah, that's right. Yeah. So
yeah.
So just to understand correctly, so you basically have, you could think of this as a system with L sites, right?
Exactly.
And then, so what is N then? Is it this?
N is it's a finite system. Okay. So you don't go into the thermodynamic limit.
But isn't L finite size of the system?
Yes. So L is a number of sites. Okay. Yeah. So and N is the number of electrons that you'll distribute over it. Okay.
Oh, okay.
So half filling would be N over 2.
Oh, okay. Very good.
N over 2. Sorry. Yeah.
I see.
Yeah. Or you can also think about it in terms of spins, because there is this quasi-spin correspondence, as you have L spins, and the magnetization is, well, there's N that are spin up.
I see.
Same thing.
Okay.
Okay.
Very good. And then, so then you would specify these epsilon i's, and then you solve
Yes.
the flow equation for the x alphas, which are like your kind of
Yeah. So you get them. Okay. So you get the epsilons from somewhere. Okay. Let's say if this would be let's say the standard Richardson problem. Let's say epsilon is given by some band structure, let's say, or by some single particle Hartree-Fock energies, right? But we use them now as variational parameters. So there's an added layer on top of that. So we calculate, we take epsilons, initial guess, we calculate, we can see the energy. Okay, we optimize, we take another epsilon, we optimize again, etc., etc., etc. So they lose their meaning as single particle energies in some sense.
Okay, thank you.
Yep. The hybrid orbitals. As the optimized orbitals at some point in your Geminal treatment. I've always had a problem with hybrid orbitals in the context of Hartree-Fock theory because these orbitals would not be time-independent eigenstates. Matthias, okay. I mentioned the hybrid method. I don't think I mentioned hybrid orbitals, so I'm not really sure whether I understand your question, Matthias.
I guess, Stan, this is when you point out the orbitals that arise in your orbital optimization to being sp3 hybridized in your
hybridization,
method,
right?
In your method, that these seem to fall out of your equations, while in typical hybridization schemes built on HF canonical orbitals, you're no longer
you impose them.
You're no longer energy. You're no longer eigenenergies of the one electron Fock operator. Is there some? There
is no Fock operator yet.
Yeah. So there.
Yeah, there's no Fock operator. Yeah, there is no Fock operator. No, they're not eigenstates of an operator. They are the variational minimum on a manifold. Yeah.
So that kind of brings me to my question, which is,
cool.
Is there any savings if you actually start with trivially sort of, because from SCF we can always do simple, localization or orientation to create. Would there be any advantage to starting with that set of? Or
yes,
could you do that in your approach?
Yeah, definitely. Yeah. There's two different regimes, and it's really it's a can of worms if you don't put any prior knowledge into it. But you're pretty safe in the sense that it's like the Mott insulator transition, right? So you have two different phases. Either you're in the dissociated regime, and then everything's localized. And if you start with any localized wave function, you use some localization scheme, doesn't matter. Then the optimization is going to bring you pretty close soon towards your desired point. Whereas if you around equilibrium, you start from MOs. And that always saves you. It gets a little bit tricky in the intermediate regime because there's not a flat. If you tend to, let's say, if you tend to follow along one of the curves, you're not going to smoothly go into the other one. They're so orthogonal with respect to each other. But you can basically check, right, in the sense that you just need some localization scheme, you'll get there. You'll need some MOs, you'll get there. These are the costly part of the theory here, because the correlation problem is scales cubic, but for the rotations you still need the 4 points transformations there. So no, good, very good. Yeah, no, yeah, exactly. You can use that information. You have to, really have to.
Great. Well, I don't know if there's any other last minute questions. I realize people may have places they have to be. I'd like to thank Stijn one more time, and I'm sure
it was my pleasure.
Happy to address any questions that people might have after the fact, either via email or Twitter, for those who.
Yeah, active on Twitter. Very active on Twitter.
So join me in thanking Stijn one more time, and I guess That's the one problem with these seminars via Zoom. You don't get applause or table
Oh,
ranking.
it's fine. It's
So,
fine.
and
I
I
miss
hope
you.
you,
Yeah.
I hope you join us in a couple weeks, because we're going to have one of Stain's collaborators. He mentioned Paul Johnson from the University of Laval,
Ah, okay.
who's going to speak on, I think, potentially some connected topics. And there again,
Yeah, I think you're
connections.
going to dig in more into the mathematics of this because I like Slavnov theorem. I just flashed it. This is a whole
Yeah.
machinery. This is
Yeah.
really a
And
whole machinery.
hopefully
Yeah.
people can see the connections now between
I
theoretical
hope so.
chemistry and
Yeah,
condensed matter.
it is
physics.
useful.
Yes.
Oh yeah, no,
There's a lot
definitely.
we can learn from each other. So great.
No,
Well,
it
thanks
is.
very
Yeah.
much. And I don't know if
My
Joseph
pleasure.
has any last words that he has to say. And
No, I'll just say, yeah, so thanks very much, Stijn. So I will now turn on the recording and I'll close the meeting. So thanks again, everybody, for coming.
thank you. Take care, everybody.
Thank you.